In this session, we will be discussing an important aspect of ligand substitution reactions, which is kinetic and thermodynamic stability. Okay, first of all, we need to understand what are ligand substitution reactions. As we know, in case of coordination compounds, a metal is coordinated to different ligands or attached to different ligands. When one or more of these ligands get substituted by other ligands, it is a ligand substitution reaction. So how do we measure the kinetic stability? Firstly, the rate of these reactions can vary immensely. There are some reactions which occur really fast and they get completed as soon as we are mixing the reactants. On the other hand, there are reactions which are very slow and they take years to complete. So, on the basis of this rate, we can define a coordination compound as kinetically stable or kinetically labile. Kinetically stable is also called kinetically inert. So if the T half of this substitution reaction is less than 30 seconds, then the compound can be called kinetically labile. And if the T half of this substitution reaction is more than 30 seconds, then it is called kinetically inert. So this is how we are defining the compound in terms of its rate or how fast the reaction is completing. Now, how do we define it as thermodynamically stable or thermodynamically unstable? That can be defined according to the formation constant. And one important thing that we need to understand is kinetic stability and thermodynamic stability are mutually exclusive. That is, they are independent of each other. They don't depend on each other. A compound can be thermodynamically labile but kinetically inert, and vice versa. So another important thing before we move on to the difference is these kinetically labile compounds, the ones in which the reaction is really fast, in those cases it's very difficult to study the reaction. You need specialized equipment, and there are various procedures such as stopped flow arrangement, T-jump, P-jump arrangement, and those are much more difficult to carry out. On the other hand, for reactions of kinetically inert coordination compounds, you can study them using various very common techniques such as UV visible spectroscopy, NMR spectroscopy, polarimetry, and so on. So it's evident that the amount of data that is present for the reaction of kinetically inert coordination compounds is much greater than kinetically labile compounds. Now moving on to this difference of kinetic and thermodynamic stability. In order to understand it better, I have put forward this table. Look at it carefully. There are a series of cyano-complexes, and over here there are the formation constants and the exchange rates of the reaction of the substitution reaction of these complexes when they are placed in water. That is the aqueous solution of these complexes. Let us go one compound at a time. So for the first compound, you can see that the formation constant is 10 to the power 30, which is a high value, indicating that it is what? Thermodynamically stable. The exchange rate is very fast, indicating it is kinetically labile. So this compound is thermodynamically stable and kinetically labile. Moving on to the next compound, 8GCN42-. Again, it has a very high value of beta and it is very fast. So this is again a compound which is thermodynamically stable and kinetically labile. FeCN6-3-. Again, it has a high value of beta, so it is thermodynamically stable, but over here the exchange rate is very slow. So it is kinetically also stable, kinetically stable or kinetically inert. For FeCN6-4-, it is again thermodynamically stable and kinetically stable. PtCN42-, it is thermodynamically stable and T half is 1 minute, that is the 1 minute which indicates the T half is greater than 30 seconds. So this is again kinetically stable. So as you can see, there is no direct relation between the two. That is, a compound needn't necessarily be both kinetically and thermodynamically stable. Now, what is the experimental implication of this? For example, let us consider 8GCN4 2-. This is thermodynamically stable and kinetically labile. So, if we take an aqueous solution of 8GCN4 2-, what it essentially means is that in aqueous solution, it exchanges ligands many times each second, but the entering ligand will always be Cn-, not water, which is more abundant in solution. Okay, it is exchanging many times because it is kinetically labile, and the entering ligand is always Cn- because the formation constant of this compound is so high. So this is the actual experimental implication of it. Hopefully the difference between kinetic and thermodynamic stability and its implication is clear, because this concept is required for all further study of substitution reactions. In the next session, we will move on to specific cases of ligand substitution reaction in octahedral and square planar complexes.